So we'll start with the colloquium now. So today I'm very happy to introduce Professor Carlos Bertulani. He's a Brazilian-American physicist, theoretical physicist, that he's been working in two different fields in astrophysics, mainly nuclear astrophysics and nuclear physics. He got his PhD in Germany at Bonn, and he did also a postdoc in Germany, in Jülich. And then during his PhD, actually, he worked in a topic which is actually very popular in nuclear astrophysics and low energy physics, which is this giant dipole resonance that he was the one that discovered and is very used in many calculations. And then he got a position in Brazil at Federal University in Rio de Janeiro. You know, as a theorist, I noticed that theorists, travel a lot, probably more than experimentalists. Yes. and he has actually many research positions, too many, so I don't think I can list all of them. But he was a research professor or visiting professor, or associate professor, not just for 1 or 2 months, but sometimes for 2 or 3 years, or even more, in Wisconsin-Madison, in GSI, in BNL, Michigan State, in Arizona, in Oak Ridge, in many other places. But he is a professor, full professor in several years in Texas A&M Commerce. He is also famous for some books that he has written in nuclear physics and nuclear reactions. I heard the book on nuclear reaction is one of the best reference that we have today, which is going for next edition. And he has received many awards, including the APS Fellowship, the Fulbright Fellowship, he's an Emmy Professor in Germany, and he also got the Guggenheim Fellowship. And I think Carlos, one thing that characterizes that he has done a lot of service for the community. I think he's one person that works heavily on the community, not just in the astroparticle, astronuclear, and nuclear physics. He is being chair of the NSF GRF position, so if we have any graduate students that want to know some input, he was the chair of this committee for a few years. And he was the chair of or very active in the Committee of Education for APS, for the International Forum, and he's also the chair of the APS Texas section. And actually he has collaborated with KU. He has a paper with Professor Michael Murray, and as I said, he is helping a lot in the community. He's a person that goes and tries to see who is the new faculty in astroparticle physics and nuclear physics, and he spent time talking to them. And actually, with Carlos, we organized a conference together in Seattle. And so it's very special, I think, for me, I think for many of us to have him here. So let us welcome him.
Thank you very much. 5 minutes of my time is already gone. Maybe I can use another few minutes to talk about you. I have had the pleasure to meet your department head, and we talked about big things, because a department head can only talk about big things, right? Climate change and women in physics, many things which are of relevance for this country, for the future of science. A very knowledgeable person. Then I'm very grateful to Daniel to come here. I got many questions of people saying, is this the second time you have been here? I said, no, this is my first time. I was waiting for Michael to invite me, because I invited him for a colloquium in Commerce about 10 years ago, and I never could come here because I will continue talking about you until he invited me here. You see how life is. In the end, I got to here. I had 2 students I met during lunch, and Jen and Justin. It was very nice. I do not know who are their mentors, but I would ask especially for Jenny to support her as much as you can. She seems to be a very knowledgeable girl who has a good future if she stays in science. I had meetings with Michael talking about physics that we have done a long time ago together. I had meeting with Allison, and we tried to find out what we know about neutron stars together. We came to the conclusion that we do not know much. I should know a little bit. That's the topic I'm going to talk about. I had a meeting with John Ralston. I would say you should be proud of having him here because he is a person who is always looking for new ideas, new things, and it reminds me very much about the Russian school in which people are challenging things, okay? At least in the past, now they are in trouble with science, and John reminds me of those, that school, that kind of school. And I think that's the people I met so far, and thank you very much for this good time I have had here so far. So, Commerce is a university which is part of this system, 9 universities, and it's the second largest in the system in Texas, but it's still much smaller than the flagship university that we have in College Station. Now, the problem with these universities is that they are small. I have to teach 2 classes per semester. But in the end, these 2 classes per semester is like 1 class you have here because the number of students are small. We have the privilege of having graders, so we only have to go to the classroom and teach. So in the end, my teaching duties are more or less the same as you have here. So it's a great place to be because you are not surrounded with so many intelligent people as you are here. So you feel less pressure. You can do things that and if you have idea, I don't need to go to conferences to have ideas anymore. I will die and many of my ideas will die with me. So I just need to be in a corner where I'm supposed to work and have peace to work, and I'll get things done. Okay, so being in a small university, especially for the students, when you apply for positions, when you go to a small university, it's not that bad. You have to look around and find out what you can do there. So I'm very happy to be in Commerce. I'm not so happy that I'm living in Dallas because for me it's completely tasteless place. My life is sitting in a sofa on Sunday, Saturday, doing calculations and watching European Soccer League, okay? And I go to the supermarket, I go to the shopping center, and then I go to university to work. That's my life. It's not very exciting, right? Then I have the conferences and collaborations. I go abroad, and that's when I have fun. I visit places like Heidelberg or Turkey or Polynesia. That's the life of a physicist. It's not so bad, even if you live in Dallas, right? Okay, so the topic of my talk is this, and I only have now 40 minutes before there will be a horn, right? Something like that, which will warn me that I'm about to end. But please stop me for questions if you want. I have many transparencies because, of course, if you work in an area like that for 30, 40 years, you have a lot of things to talk about, right? I don't work in this area for 30 or 40 years, but a few years, but I already have a lot to talk about. So I was in Russia many times, and I like their style. And their style is such that sometimes people don't pass by the first transparency. The Russians, they say, you are wrong. You don't know what you are doing. Even the title is wrong. And I like that. It's a challenge because you don't have to watch the seminars in order to, you can just discuss things. So please stop me. And if I don't show everything that I need to show, you didn't miss much because you have already things to do in your area, your expertise, right?
I'm Russian.
You are Russian, okay. So I wait for you. Privyet, spasiba, na zdоровье, spasiba, and all those words that I cannot, Russians, I love. No, I said good things about Russians. I said they like the style, is the challenge things. Some people think you are offending when you say, this title is wrong. No. Let's discuss about the title. I don't think it's wrong, my title, but there are titles who are, which are wrong. Okay, so let's talk a little bit about this. It's physics that probably you don't know is low energy nuclear physics, sometimes associated with what we call high energy nuclear physics. But because Justin and Jan who asked me, I think I Jen is hiding there. They asked me about what is exactly what this nuclear astrophysics is about. I put some transparencies there just to show you what we are doing in this area. So these are collaborators. This was my thesis advisor. This is a dean, you can see from the tie. This is not a dean, but it's Japanese. It's very typical in Japan to use a suit, even if you are not a dean. This is a big boss in Germany, $3 million per year, 3 million euros, and lots of people. This person died recently, a very good collaborator in Brazil. This is also a great physicist, Polish physicist living here. Peter is also an experimentalist in Germany, in Darmstadt, and he is a brilliant theorist in Seattle, doing low energy nuclear physics. And these are, you see, even if you live in Commerce, Texas, you can have postdocs and you can have students, and you can take pictures of them proudly in front of our flag, right? So, or our map. So these are students who have helped me together in this work, and I'm proud that some of them are now in good situations somewhere. Okay. Okay, so what is that nuclear physicist, nuclear astrophysicist? There is a label called nuclear astrophysicist. What does that nuclear astrophysicist do? They do nuclear physics. Okay, so in the old times when nuclear physics, like in the 60s and the 70s, was a big thing, and the department heads would like to hire them because there were these millions of dollars being channeled, fueled to nuclear physicists, nuclear physics, and it seemed to be very important to hire these guys because you wanted to have some overhead on those on that money. These guys were calculated some 2+ level, 0+ level in oxygen 16 or calcium 40. Now, if you want to try a guy like that, who cares, right? The 2+ level is in 2.13 MeV above the ground state or not. Who cares about that? So what nuclear physicists are doing right now, most of them are doing the same thing these guys were doing at that time, but now, since they found out that it's very appealing to say that you work with the stars, and all your PRLs and Nature papers, they have this introduction, this 2+ level is important, otherwise the stars would not be what they are, you get it published and you get hired, maybe. Okay? So what we do is still nuclear physics, and what we do, and we gave stellar models, is this here. So if you're a stellar model, you want to know how energy is generated in a star and how elements are formed and why we have this amount of elements and isotopes or whatever. This is one of the big questions for mankind, one of the 10 big questions. Why the abundance of elements is what is observed, okay? Yes?
What are the other 9 big questions?
Oh, dark matter, dark energy, dark you, dark me, and dark everybody. Okay? People like dark things nowadays, right? So everything related to dark, well, but there are other questions. I'm sorry for people in solid-state physics or condensed matter physics that there are many questions about high-temperature superconductivity and many interesting things which will be of relevance for mankind. It's among these 10 questions, okay? Okay, so this is what we call elemental abundance, okay, of a certain species in the stars. Think about calcium, whatever isotope. And it can decay. These are numbers associated with density and of particles in a certain stellar environment. And this, of course, to first linearly, it's proportional to the number of that species that decays into this species here through a constant, which is the decay constant. So nuclei decay, beta decay, they emit particles and so on. So they can be transformed from this I, J to this I here. Okay, this is one of the equations. The other is how they are formed. 2 of the nuclei, J and K, can get together and form nuclei I. And it also involves a product of densities, some counting, statistical counting, which are in these numbers here. And there is one thing that we need to know, is this average here. This average is, you have something which is called a cross-section, and any soldier knows what's a cross-section, because when there is a war, you just jump to the ground, right, to decrease the cross-section for a bullet coming to you. It's just that area, quantum area, where something happens, and that's what experimentalists do. They are building these facilities, billion-dollar facilities in the United States, to measure cross-sections of these two guys weighted with the velocity that we expect is well described by Maxwell-Boltzmann distribution. There are questions there because Maxwell-Boltzmann, the Boltzmann-Gibbs statistics, we assume that it's perfect and explains everything, all thermodynamics, right? But there are questions there why it really works, because it assumes that we don't have memory effects, we don't have long-range interactions, and so on. And then we assume that this works well in stars. If it works well in the stars and during the Big Bang, then we can try to reproduce the experimental observations about the elemental abundance in the universe or in the solar system and so on. So what nuclear physicists do is that they provide, either theoretically or experimentally, these quantities here. This is the reaction rate in going from JK to I. So the reaction rates at a certain temperature, as I said, if you assume that Maxwell-Boltzmann distribution is good, and there are questions about that, okay? It might not be, you might not think it would, there be questions about it, but there are questions about that. Then for a certain two different temperatures, you have the peak of the distribution, as you know, located at a higher value if the temperature is larger. And this is just to show you something that I lived in my life and the young people didn't, which is PowerPoint presentations. PowerPoint presentations make any idiot look good, including me. Because you download these nice pictures from the internet, you download movies from NASA, and then you give a talk, and people say, that was the best talk I ever watched in my life. And basically, you didn't do anything, okay? So I was from the time in which you used transparency and that thing there, the blackboard. You'd go to the blackboard, and you would derive things slowly, okay? The students give bad evaluation for faculty because of PowerPoint presentations, or keynote presentation, or whatever you call it, because you go too fast. And then at the transparency 10, they already forgot what was in the transparency 1. In my time, you had a blackboard, and you could see what was derived before. So PowerPoint presentation, I do not really know if this is good. I think the human brain cannot see things, hear things, and process things in the same time. Okay, so it's something for you young guys to think about how is that we evolve with education in the future, we make people learn better, okay, because I think we are kind of making problems with this kind of things. You see my transparency, isn't that beautiful? I am such a nice presenter, right? Okay, so now you see, I put some effort doing these boxes and things like that. So nuclear physicists, they calculate, for example, for a certain nucleus, this sort of reactions here, or they measure it, and they give to stellar models to calculate the reaction rates, and this is the quantity, the weighted with the relative velocity of the ions in stellar plasmas with the Maxwell-Boltzmann distribution. This is a double count, just to prevent that you double count. And what you have is that what happens is that the cross sections, except for the ones involving neutrons, almost everything you have in the stars have charge. And charge repel, and it's very lucky that we have this tunneling thing, 90-88 gamma, that prevents the sun to burn like this, poof, in a second. Right? That's why the sun is there for billions of years, because of tunneling effect. The cross-sections are very small. And what we have is that the cross-sections drop a lot, okay? And this is Maxwell-Boltzmann distribution, enters here, okay? And then you have these cross-sections. Because of the tunneling, it takes such a long time, these cross-sections are very small. This probability that two particles, like an alpha and something else, come together, tunnel, through the barrier, is very, very small. So you have an overlap area in this integral here, and this overlap area is called the gamma of window, and it has a gamma of peak, and it's at very low energy. So here you have the Maxwell-Boltzmann distribution, and only the tail of the Maxwell-Boltzmann nuclei in that tail will react and will enter this integral here. And this causes a big problem for low energy nuclear physics. So basically, in order to get the cross sections and the reaction rates are like this. The cross sections drop, and you need, for the stars, for example, in the sun, you need cross sections at 20 keV of relative energy between the particles. 20 keV, to measure some of these cross sections is almost impossible, okay? Because the number of events that you are going to get. You have an intensity, and it's very easy. What's the number of events? Just multiply by this cross-section. And then you get the number of events. And if you have to run an accelerator, nuclear physics is very expensive because you have to build these big accelerators, okay? You have to put a lot of energy to penetrate the atom. This costs money, okay? Millions or billions of dollars, okay? And you cannot run an accelerator for a year to get 1 point. Statistically, this 1 point means nothing, right? So that's the problem. So what they do, and this is all because of tunneling effect. You can think that the cross-section is this area. This 1 over E is area. Why is area? Does anybody know why 1 over E is area? 1 over energy. E is energy between the particles. Because any cross-section is a quantum area, pi lambda square, right, times the probability that something happens, right? This gives you the cross-section. This quantum area, pi lambda square, de Broglie says that it's proportional to the inverse of energy, right? Lambda square goes with energy. So this is nothing else than phase space. This is a rough account of the penetrability through the barrier. Okay, this was introduced a long time ago, I do not know, by Hans Bethe or so on. And this is where nuclear physics is. When they penetrate the barrier, something happens inside here. And so what they do, the nuclear astrophysicists or people who run these $1 million laboratories, nuclear physics laboratories, that they do not measure this that they need for the stars. They multiply this, what they measure by this factor here, the inverse of this factor, and by the energy, and they get something which is called astrophysical S factor. So in astrophysics, there are many S's. This is one of them, okay? S factor. And so they have here the experimental data, and they ask Carlos, me, to run a theory for that reaction. And they say, Carlos, can you do some calculations? And then I do some calculations, and they extrapolate or interpolate this, extrapolate the cross-section to this gamma of energy, which is at very low energies, where they cannot measure, okay? The problem is that my theory, and I'm proud to say that, most often I am wrong, okay? Because my theory is not perfect. And I miss some resonances. Quantum systems display resonances. I miss some sub-threshold bound state resonances. So this data that they get here might be completely wrong, okay? Using my theory to extrapolate to these low energies that they need. So it's a very expensive thing, nuclear physics, with these laboratories. And let me give you some example here. This is one thing that we nuclear physicists are proud to say. When a supernova explodes, it leaves behind a black hole or a neutron star. Depends on its mass, okay? And what determines if it leaves behind a black hole or a neutron star is one of the things which is relevant to answer this question is there's a reaction here. Now you can imagine a tiny little thing, a reaction in nuclear physics, can have a very important role in answering what is the density of black holes in our galaxy, what's the density of neutron stars in our galaxy. And you can trace to this reaction here and say, if this is wrong by 20%, we cannot answer this question. That's what some astrophysicists have told us. And look what nuclear physics get for the astrophysics S factor. So they get data, but they need the cross-section at 300 keV at many stellar scenarios. This is 1 MeV, relative energy, and we need here. But these cross-sections here The photon here carries dipole and electric quadrupole multipolarity. And you can do some reactions which you can trace to these different multipolarities. But you need to extrapolate here to this region here, and this scale is logarithmic. So we are really in trouble because we are never going to go to these energies here. It's too expensive. People already have tried a lot for decades and decades, 40 years, 50 years of nuclear physics. And it's too expensive, and especially, for example, here, and we don't really know what's going to happen here. So we rely completely on theories in nuclear physics in some of these questions. What's determining the density of black holes in our galaxy? And then I trace back to this cross-section here, nuclear physics, okay? Okay, so why nuclear physics is so important? That's why I wanted to ask this question, what is nuclear physics? So you have here in your laboratory here in your university, Michael Murray, Daniel Tapiatakaki, and others who work in CERN, and they do experiments at TeV per nucleon, very high energy in colliders. They do these experiments at CERN. And what they want to look at, and again, I go back to why you are doing this. I'm doing this because I want to answer something associated with the existence of the universe. And if you say this in a cocktail party, people get really impressed. So you are useful, right? So you're a guy that science needs. That's why probably Michael, who is sleeping there, will tell you in a cocktail party, I want to describe if the quark gluon matter it really existed during the Big Bang or compact stars and so on. And then you have the other range, which is very low energy. So for here, you need an accelerator which like LHC or other which might come. And it's very expensive, as you know. The operational cost of CERN is $1 billion, 1 billion euros. Now we have all this faculty around the world, like Michael, Daniel, and thousands around the world. Now that's how you should do the calculation, okay? I always tell my wife, sit down and do the calculation before we enter this discussion, right? So people don't sit down and do the calculation. How much does it cost thousands of professors around the world? $100,000 per year or $200,000 with benefits and whatever? Multiply by 1,000 and you see how much does it cost per year, all these professors, and add to the CERN account because that's what they are doing, right? So it's a lot of money put here, not so much put here, okay? And the difficulty here is that we don't really know what to do, okay? How we improve the intensity and how we battle with tunneling. That's tunneling the problem here. What happens in the sun, what happened during the Big Bang, what happened in stars right now. They're battling with tunneling, which is a very simple thing. And it costs a lot of money to improve this scenario here, and we don't have any ideas. And I told some people here many times, you can always ask why we are spending all this money with these scientists, crackpots in University of Kansas or Commerce or whatever, giving them money, millions and billions of dollars to study the stars, if we don't have the cure for cancer. And the answer is very simple. You know what's the answer? Jen? You don't know what's the answer? The answer is you don't give money to people who have no idea. So you go to a hospital, you give $1 billion to a doctor because he's studying cancer. What's he going to do with this $1 billion? He's going to waste. He's going to hire his wife. He's going to travel around the world. He's going to do things which are completely... So what other countries have observed what United States had observed already in the beginning of the century, that's what made this country so great, is that investing in basic science, like investing in a guy, crackpot studying string theory, these are all interconnected. This brings from several directions technology and knowledge, which will end up in the study of cancer with new gadgets, with new things. It moves the whole science, okay? That's why we need to invest in these areas which, like this, like nuclear physics, cosmology, stellar physics, and so on. I think I'm giving you some justification for your existence, and you are quite sure that I don't have to say that because you know that very well, right? But why is this problem here and this problem here so difficult? Because nuclear physics is not for everybody. Okay, nuclear physics is very difficult. Why? Because we have these nucleons, okay, and they are made of quarks and gluons, and there are some basic properties that we don't know, like the spin of the proton. Why is like that, okay? And people think, well, it's motion of quarks inside and so on, but we don't really can explain it, okay? So there are many problems in nuclear physics. How do you pass from these quarks and gluons to the nucleons interacting outside the nucleus? How do we break these eggs and make quark-gluon plasma? How does this physics here has to do anything with quarks? Okay, it's very hard. QCD, we are making huge progress. It will take 100 years to solve. Okay, even with the so remember the computer in Hitchhiker Guides to the Galaxy? The answer is 42. So we will take 100 years doing these calculations, and we really don't know how to proceed, okay? So only by having some new ideas in the future. It's very hard science. Okay, having told you that, I already told you about this. This is one of the greatest challenges. Alison asked me what are the other greatest challenges to explain the abundance of elements. I gave two. But let's go to neutron stars. Well, neutron stars is a different kind of physics. Let me tell you one thing. I have many nuclear physics colleagues in the world. They were doing nuclear structure, that 0+ level in oxygen 16, who nobody cares, or 2+ level or whatever. And now they are all doing neutron stars. And I will tell you why is that. First of all, it's sexy. If you tell in a cocktail party I'm studying neutron stars, people will say, wow, the 2+ level in oxygen, nobody cares. They will go and talk with other people, right? So why you are doing neutron stars? Because of that. And second, because there are only very few observations about neutron stars. Masses, radii, they have glitches, okay? Not much more than that, which means as a theorist, you can do whatever you want because nobody can say that you are wrong. So theorists like to sit and think about strings and things which are not measurable, and you project the wave function of the moon on you and ask, what is the probability that the moon is inside of you? A theorist can do that. He'll tell it's 10 to minus 500, but he'll give you a number because he can make a model for that, but is that useful? So the lesson I want to give to you is that many people are doing this kind of things because they can use their imagination and do whatever they want, okay? Now, it's very hard to explain experimental data that we obtain here on Earth with nuclear physics and you don't get to publish Nature, you don't get to publish physical review letters. So what's the point? Let me study neutron stars because everybody's talking about them. So they are supposed to be remnant of large mass stars. This is the solar mass. We think that there are 100 million in our galaxy. Well, these numbers, they change. We think that their masses is within the range, and if there are masses larger than this, they will collapse to a black hole. The largest observed is in the range of 2 solar masses. They spin around because whenever you go to the South Pole, the thing turns in one direction. Wherever you go to the North Pole, the water in the sink turns the other direction. This is completely wrong, okay? It doesn't work like that. The hurricanes work, but not in the sink, okay? But we know that angular momentum is very important for hurricanes, for example, and for everything. So everything rotates because initially they had some angular momentum. When they contracted, they keep the angular momentum, okay? So this happens with neutron stars when they are leftovers of supernova. They have enormous densities, okay? And one of the things in astrophysics is that you play with numbers which are 10 to minus 23, Avogadro. Nobody understands what's Avogadro number. So Michael, wake up. So how many molecules of whatever? Archimedes, 3,000 years ago, he went to the beach and he relieved himself. A liter. Now these molecules of the Archimedes, whatever it is, went to the atmosphere, rivers, they homogenize with all the water in the world. Question for a student: how many molecules of Archimedes P is in this cup of coffee? It's a rough calculation that you have to do involving Avogadro number. How many molecules of Archimedes P?
It's a few thousand, isn't it?
It's like 100. And then when I tell this to students, they say, ugh! And then you have to tell, well, water molecules are clean, okay? So these are the water molecules. But Avogadro number, nobody understands what it is because it's 10 to 23, right? 10 to 23 molecules. You can understand numbers like 10 to 23. So astrophysicists, they talk about 10 to the 40, 10 to the 50, 10 to the minus 23, 10 to the 23. You get completely lost. So the only way you can really understand these things is try to make some comparison. If you put the matter of neutron star in a matchbox, it would be equivalent to the weight of 10,000 Empire State Buildings. Now I understand. Well, kind of, right? It's still hard to understand such large numbers. The pressures are also, look, 10 to the 34 pascals. You know, and even people make you see, Interstellar movie. So a physicist helped to do that movie. It's so full with flaws because that guy goes to a neutron star and many years passed by. In fact, if you go to the surface of a neutron star close by, only very few change in the time will happen. Proper time, right? The proper time there is not very much different than an inertial frame of reference. It would change just a little bit. But the movie was guided by, who was the guy? Kip Thorne, okay? So even the movies, there is spaghettification. If you come close to a neutron star, you'll be stretched. But that thing about time is all wrong, okay? So there are things that even when you try to make in science fiction, it doesn't work quite well. They were discovered by accident and by hard work by Jocelyn Bell, and you know the story very well. She was a student in England, and she discovered it in 1967. So it was radios coming from spinning stars called pulsars, and because we don't like and we don't treat women so well in science, she didn't get the Nobel Prize, but her advisor, who is a macho man, no, I'm just kidding, he's a man, he got the Nobel Prize, okay? Maybe if it was the other way around, the student would get the Nobel Prize, not the mentor. And that's what I was talking. Neutron stars is a compact object. It has like an outer crust made of atomic nuclei, free electrons. And as you go inside, you form strange structures. There are people who work with pasta nuclei in neutron stars. And for example, one of the questions you want to see, for example, inside at the core of neutron stars would have a kind of cold quark gluon or other exotic objects there. So this is Jocelyn Bell. She came to Commerce. She didn't come to the University of Kansas, right? But she came to Commerce because of us. She found out that we are good. And I have to visit this place called Commerce, Texas. She came there in 2010, and she's a very pleasant person, extremely pleasant and very humble. Okay, we talked a lot about her findings, and she's not really an arrogant person who says that I discovered this thing as others. And she wrote a preface to my book. It's not really my book. It's an edited book together with Jorge Picarevics, who is a professor in Florida State University. It's a collection of very good nuclear physicists or astrophysicists in the country and even outside the country. And she wrote a very nice preface to this book. And this was about in 2011 after she visited us. Okay, now I have 10 minutes. And you know what? I didn't come to what I wanted to talk about. And what I'm going to talk about will not really interest most of you. So let me make a 10-second reflection. What should I talk about? Okay, because 10 seconds, okay? Because I have 70 transparencies. We are number 17, okay? So how do we relate this physics of what we see on Earth? Because as I was talking to Alison Kirkpatrick, we cannot only rely on these observations. There are things like neutron stars and even the sun, okay? How do you know the sun has 15 million degrees inside? How do you know the density is, how much is this, 150 grams per cubic centimeter? How do you know all that, okay? We have to have a probe, something coming from inside. Neutrinos is a good probe. It tells us about if our calculations are correct for the sun. But neutron stars, there are so many, there is nothing really coming out of a neutron star. There is the magnetic field that we can observe and things like that. But it's very hard only relying on astronomical observations to describe stellar objects. So you have to do some experiments, okay, like what Michael and Daniel are doing in CERN about relativistic heavy ions. So here I have something to tell you in 10 minutes, which will be 50 transparencies in 10 minutes. And this is about this thing that you can do in neutron-rich nuclei. What we are doing in nuclear physics, and we are going to build a laboratory in Michigan State University, is that we are studying nuclei far from stability that only live like milliseconds, and they play a role in the stars. But on Earth, they don't play any role. They don't exist, only artificially. You produce them in flight through fragmentation, and then you try to study them in flight by throwing them against a target. That's the hard life of a particle physicist and nuclear physics experimentalist. There is only one thing you can do, an accelerator with a beam and a target. And then you put your detectors to see what happened, to calculate or to measure those cross-sections. A very hard life for nuclear and particle physicists. It's not easy to get experiments done because, in contrast to theorists, that they can do whatever they want, okay? That's all that you have in nature. But unless we do that, we will never answer those questions which are relevant for mankind. Why are we here? Why we are made of these elements? Why neutron stars are like that? Because we are not going to have probes which are much better than what we already have now in astronomy. So we did do this kind of things. We study, for example, excitations of light nuclei. Rich in neutrons, they decay very fast. You can only produce them in accelerators and study them in flight. And we try to connect with some sort of easy physics. This is the DIM, by the way, that I told you. Simple physics like the response to certain operators, like the response to a photon field, and try to connect to the data. And we talk about this pygmy resonance, which is in contrast to giant resonance, are resonances in which the neutrons are so loosely bound that they form like a background. And by finding out what is the energy deposited in the nucleus, you can make connection to neutron stars. Can you imagine that? You connect with a few neutrons to something which is very large, like 10 to 55 neutrons. So I have worked a lot. This is more or less like advertisement of my work. I don't want to go on that. This is just to show that nuclear physics is difficult. There are problems that are associated with interactions, the final state interactions. Perturbative theory doesn't work very well. You can do, try to connect to QCD, and the way that many physicists got, nuclear physicists got jobs in the United States is try to sell the idea that QCD is very difficult. We are probably not, nobody in this room are going to get the answers for why a nucleon is like this from first principle, why the deuterium, why a heavy nucleus is like that by solving the QCD Lagrangian from first principles. So people try to do some sort of bridge. And one of the bridge is called effective field theories, which include the interactions in terms of what we need coming from some information from the quarks. It's very different than low energy nuclear physics done by many theorists, because many theorists, low energy nuclear theorists, they do solutions of Schrödinger equation. You have a potential between the particles. You give me the potential, and I give you the results. Even computationally, this was a challenge in the past. Nowadays, we are doing ab initio nuclear physics, in which give me the interaction, I put in the computer, and I give you the answer. But I need a supercomputer. I need $1 million. Scientific discovery through advanced computing. Give me millions of dollars, and I'll try to solve this problem, which is relevant for everything. in nuclear science, like bombs, like nuclear medicine, like why we exist, why elements are like that. So all these answers I can give you if you give me the best computers in the world. Okay? So this is one of the things that we are trying to do. The other thing is to try to connect to quantum field theory, which is a completely different aspect. Instead of solving quantum mechanics, you solve Feynman diagrams. And then you solve problems like regularization, renormalization. In the end, you get the same results because nature is the same. It's few nucleons interacting. Okay? But you try to bring this fudge factors and connect these fudge factors with the physics inside the nucleon, the quarks and gluons. So this is the connection to the QCD. So you do all this, and then you get some results, like, for example, the scattering of neutron on helium-4. I will not go into details. Or the structure of some nuclei. Some of my colleagues are working effectively on that. Well, going back to the DIN, okay, so we are looking for very complex nuclear physics calculations we call random phase approximation, and there are several sorts of random phase approximation, which is something that we adapt from solid-state physics to nuclear physics in the 50s, and we still do it, okay? And we are looking for this small peak at low energies, which is associated with pygmy resonances. We have done works involving clusters in nuclei, and we have compared to the case of giant resonances. Giant resonances in nuclei was the last Nobel Prize in nuclear physics. Okay, there were other prizes in nuclear physics, like in '84, Willy Fowler. This was nuclear physics disguised in terms of nuclear astrophysics. That was a Nobel Prize for us. Then there were some neutrinos prizes, like a few years back, 15 years or so, that were also based on nuclear physics, but we don't call those guys really nuclear physicists, okay? They were more like neutrino physicists. So in order to detect the neutrinos, you need nuclear physics in the end, in many of these experiments, not all. So the giant resonance occurs at around 20 MeV in nuclei, but this pygmy resonance, they should absorb less energy because it's easier to excite the nucleus in this way. That's what is the pygmy resonance. I will not go into all the details, but look, if we as a mankind want to answer this fantastic question, why there is so many of these elements and so less of others in the universe, okay? Can you explain me? My grandmother can ask me this question, and I would be embarrassed. You have worked in nuclear physics for 100 years, and you know how to solve this. My grandmother was pretty tough until she died, okay? So it's embarrassing for nuclear physicists to produce something like that. What is that? This is the relative abundance of elements. And there is a process called rapid neutron capture in the stars, which occur, for example, either in supernova or neutron star mergers. And they are supposed to be the producers of heavy elements, okay? And we are trying to answer questions like this. And these are theoretical calculations. And you see that this is a guide to the eye. And these are and these are observed abundances. And when you have these pygmy resonances or giant resonances, you go from this sort of theoretical prediction to this sort of theoretical prediction, because the energy as the nuclei absorbs in this explosive scenario is very important. If you have these pygmy resonances, they can absorb energy, and the abundance of elements go together with that. Those first equation that I have shown goes together with that, because, and then you see you change completely. And that's where we are after 70, 80 years of nuclear physics. I have a lot of things to show you, and there will be the thing that should I wait for the gong? You said there will be a gong, 10 minutes. I see 10 minutes there. Sure. Isn't that beautiful, guys? How much we depend on knowledge of people like me, nuclear physicists. You'll never be happy if you don't answer those questions of the universe. So you need a guy like me, like Michael, like Daniel, and John, to do this kind of physics that without them, you are not going to, Allison, you are not going to be able to answer, okay? How is that these objects which interact microscopically through nucleons, through whatever they are, quarks and gluons, end up shaping life. right? The triple alpha reaction, you know that very well. Without a certain resonance in certain place, it would not exist. And this triple alpha reaction is just a nuclear physics thing, right? Okay, so I will go on. If you want to do neutron stars, you can do this on 1-page or 2-page code, preferably in Fortran, who nobody likes. Everybody says that you have to learn C++. I did. I did learn C++ 20 years ago. Completely useless. Because C++ is like you have a cannon and you try to kill a fly with the cannon. Okay, it's a lot of resources that nuclear physicists don't need. Nuclear physicists need, or physicists in general, if you're a theorist, you need to solve differential equations and integrals. And for that, you just need some very simple language in which you do a do loop, you do an if to avoid some things, and nothing else. Now you have all these containers in C++. Why do the students want to know that? Because it's cool. I have heard that it gives me a job in the industry. Okay, if you want to invest on that, that's okay. But for nuclear physics to get a plot of y versus x, that's what you need, and compare with data, you just need some, Python is okay. Python is very useful. You do these calculations, and you can also do more with Python. I would recommend that you learn Python. But this code in Fortran or even in Python, you can do in two pages. So you have the pressure. This is hydrostatic equilibrium in the star. These are components which come from general relativity and special relativity. Otherwise, you just have one here. This would be the sun. And this is the mass composition, just mass composition. These are coupled equations because one depends on the other. M enters here and appears here. So you have to solve this coupled equation. Runge-Kutta method, very simple, so small. And then you solve this problem. But you need something. This pressure here, you need the pressure as a function of position in the star. This is called the equation of state. And it's derivable from the energy density of particles. And the energy per particle for a certain density can be expanded into a Taylor series. And the compressibility modulus, what keeps the star from collapsing, comes from this guy here. And it's just a second derivative of this quantity here. Now we know this in nuclear physics. This is the saturation density, 0.16 per Fermi cube. This is how many nucleons are in the center of the nucleus. And in neutron stars, there will be this density too. We will pass through this density. And these are corrections when you have deviations. Okay, it's a Taylor series. You go here forever. Not forever, but if you had 3 more terms here, you have everything you need. And this is the first term which gives the how the star does not collapse, the incompressibility modulus due to gravity because of the nuclear response. And then you put this and you make these wonderful plots. And this is the radius. This is, for example, for a certain equation of state, where they come from. I can explain later. Maybe I will not have time. And then you solve it. And then you find that for a certain radius, there is this transition here. And there is this mass here, which corresponds, the maximum mass, which corresponds to a certain radius. That's how we connect now to observers like Ellison. And then we try to see if we can, from microscopic point of view, because in order to get this pressure, you have to know this quantity here, right? And how do we do it? Now comes nuclear physics. Look, this is also old in nuclear physics. So how nucleons interact inside the nucleons, the nuclei, or in neutron stars. You assume certain nucleon-nucleon interaction, and here is a very popular one. It's called Skirm interaction. It has 10 parameters. All these constants here are parameters. And then you try to reproduce some properties of nuclei, like masses. It's very hard. Huh? We have like 6,000 nuclei that we need to fit those masses and fit some basic properties of them. And these parameters are used. Now guess what? There are like hundreds of these Skirm interactions, which reproduce the same experimental data. 2 minutes. And these are what nuclear physicists do. Okay, so they solve the pairing problem, blah 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 blah. and then I go, where do I go? You try to reproduce masses with the difference in masses as well as you can. Now there is another problem, which is the symmetry energy. When you go to neutron stars, you have 200 neutrons per proton. So it's a very asymmetric neutron matter. So on Earth, we have these nuclei which have roughly the same number of protons and neutrons, but we are treating a problem which is the neutron star, which is basically neutrons, right? So we have to know this thing here, which is called symmetry energy, which is this guy here, and it can also be expanded into a Taylor expansion. And the problem is that this parameter here, the slope parameter, in fact can be between 20 and 150 with the best knowledge that we have. So the problem is that the pressure in the stars, in neutron stars, is directly proportional to that parameter. And we are trying to fix this by looking at pygmy resonances and so on. You can see this present status. At the saturation, we can reproduce everything very well. But when you go away to the center or to the surface of neutron stars, you get huge deviations for all the interactions that we nuclear physicists have been working for 50 years or so, okay? So very hard thing. We also try to couple this with effective field theories. We have huge uncertainties. And the problem that we are after now is some investment that we are doing in JLab, for example, to try to identify what is the skin of a nucleus. Can you imagine that after 80 years or 90 years of nuclear physics, we can still say what is the skin, neutron skin in lead? Okay, we have lead nucleus, okay, which is a very common nucleus. Now, what is the neutron skin? How much do the neutrons go outside? The pressure on protons and the pressure on neutrons is different. So the neutrons extend a little bit more outside. And we cannot really say how big is this skin here. And by looking at this skin, we are trying to go from this few nucleons to 10 to 57. And if you don't make this, if you don't try to solve these fundamental questions, which might seem like useless for some of you, we will not solve this problem of understanding neutron stars. Okay, so I will not go on. I will just stop here. Because as I said, I had 70 transparencies. There's a lot of things to say. But at least I have seen some faces here. I have entertained some people. Some people are looking at the computers and looking at some web pages with some Hollywood stars. I don't look like one, right? If it would be Brad Pitt, I would call attention to you. But many people looked like they were happy with some things I said or unhappy. And if I made you unhappy, I already made something good because I made you unhappy. You are upset. This is good. This is challenge, okay? This is challenge to our knowledge. And I was all the time saying that nuclear physics is very important. Some of you are particle physicists or solid-state physicists. And some of you think that nuclear physics is really not so important. And I was trying to challenge you, okay? Because we are all scientists here. And we have to respect the value of everybody. Everybody has a place here in this big scenario as why are we here? Why things are like that, and what can we do here to explain things which are there, and it's not that easy.
Thank you very much.